Nothing, the complete absence of everything. We humans believe that something must exist in order for something else to exist. But how did it all begin? We say it started out of nowhere, but nothing can't just turn into something, can it? In the vast cosmic space where galaxies shine and black holes devour matter, a mysterious concept exists: nothingness. This is not just a philosophical idea, but a fundamental part of our understanding of the universe that has always fascinated scientists and thinkers. Imagine a place in space where there is almost nothing, no stars, no planets, just emptiness. It's a bit like a quiet corner of the universe where the usual rules of physics don't work in quite the same way. Join us on a journey into this mysterious cosmic void, where we will encounter the fascinating depths of space, explore cutting-edge technology, and peel back the layers of the mystery that is nothingness. The concept of nothingness seems paradoxical, and yet it is an essential concept in advanced cosmology and science. For those who want to fathom the mysteries of the universe, understanding what nothingness in vast space really means is the first step toward unraveling the enigmatic fabric of the cosmos. At first glance, one might imagine the emptiness of space as a pristine vacuum, devoid of any matter or energy. Although this idea captures a certain simplicity, it does not do justice to the complicated reality that we have uncovered through scientific research. In modern cosmology, nothing in space is far from being an absolute void. Instead, it is a nuanced and complex terrain that challenges our preconceptions. Contrary to common intuition, the vacuum of space is not truly empty. It is filled with quantum fluctuations, a phenomenon in which particles and antiparticles spontaneously arise and annihilate each other. These fluctuations give the supposed emptiness a dynamic and ever-changing nature. Space is intrinsically connected to the fabric of space-time as described by Einstein's general theory of relativity. Even in regions with no visible mass, the presence of massive objects can bend space-time and affect the orbits of nearby objects. When we look into space, we can see the faint echo of the Big Bang itself. The cosmic microwave background radiation is a relic of the early universe, a quiet whisper that reminds us that space was not always as we perceive it today. Despite our advances in understanding the concept of nothingness, it remains a mystery to scientists and philosophers alike. Rumors circulate about the possibility of regions where matter density reaches veritable nothingness, but these speculations remain on the fringes of cosmology. One intriguing idea is that there may be regions in the universe where the density of matter is extremely low, close to the void. These hypothetical voids, if they exist, could offer crucial insights into the nature of space itself. Is empty space really free of all matter and energy? This seemingly simple question opens a Pandora's box of scientific revelations and philosophical reflections. In the realm of conventional knowledge, the vacuum of space is often viewed as a pristine vacuum, a bare canvas without the slightest hint of matter or energy. It's an appealing idea that fits well into our human understanding of emptiness. But as we delve deeper into the boundaries of cosmology, we discover that reality is far more complex and fascinating than we could ever imagine. In the world of quantum mechanics, the subatomic realm that governs the behavior of particles at the smallest scales, we find a concept that challenges the essence of nothingness. This concept is called quantum fluctuations and tells us that even in the loneliest corners of space, particles and antiparticles arise spontaneously, perform a fleeting dance, and then annihilate themselves in a cosmic instant. These tiny and ephemeral events contradict our traditional understanding of emptiness and breathe life into nothingness, creating a dynamic and ever-changing canvas. In addition, the general theory of relativity, formulated by Albert Einstein, teaches us that space and time are interwoven into a four-dimensional structure known as space-time. The presence of massive objects such as planets, stars, or even black holes can distort this structure and influence the orbits of nearby objects. In this sense, the idea of a completely empty, unchanged space becomes an elusive dream. How does nothingness relate to the mysterious presence of dark matter, and what does it reveal about the intricate fabric of the universe? To solve this cosmic mystery, we must first understand the nature of dark matter itself. Unlike the ordinary matter that forms stars, planets, and galaxies, dark matter remains hidden from our senses and reveals its existence only through the gravitational forces it exerts. Essentially, it is the ultimate embodiment of nothingness, as it eludes direct observation and defies traditional descriptions of matter. The existence of dark matter became apparent through the observation of galaxies and their movements. The gravitational force exerted by visible matter alone could not explain the observed behavior of these galaxies. To fill this gap, scientists proposed the existence of an invisible, immaterial substance, dark matter, that fills the cosmic voids and holds galaxies together. This mysterious void of dark matter challenges our conventional understanding of emptiness. She cloaks herself in invisibility and yet holds the cosmic reins that shape the structure of the universe. She is a prime example of how nothing can be scientifically significant and profoundly influential. Within the cosmic web, dark matter forms giant filaments and halos that create the framework on which galaxies and galaxy clusters accumulate. Without the presence of dark matter, the universe as we know it would look drastically different. The cosmos would lack the gravitational glue necessary to form the celestial bodies that have captivated the human imagination for millennia. The Big Bang Theory postulates that the universe as we know it began as a singularity, a point of infinite density and temperature, about 13.8 billion years ago. It was a moment of cosmic emergence, an event in which the fabric of space and time itself was born from what might be called nothingness. But how does this theory describing the explosive birth of our universe relate to the concept of nothingness? To understand this, we must first understand the nature of the singularity. At the moment of the Big Bang, the singularity represents a state in which the laws of physics collapse. It is a point of infinite density and zero volume that exceeds our usual understanding of matter and space. In this sense, the singularity can be seen as a manifestation of nothingness, a point at which the universe was stripped of its familiar structure and dimensions. However, this seemingly nothingness was full of potential. As the universe expanded from this singularity, it underwent a rapid period of inflation in which space itself expanded exponentially. In a split second, the universe went from a state of cosmic nothingness to a bubbling cauldron of energy, particles, and the fundamental forces that govern our reality. During the first moments of the Big Bang, the universe was incredibly hot and dense, resembling a primordial soup of particles and radiation. In a fraction of a second, it underwent a series of transformations, including nucleosynthesis, during which the first atomic nuclei were formed. This cosmic evolution eventually led to the formation of stars, galaxies, and the complex structure we observe in the cosmos today. In this context, the concept of nothingness takes on a dynamic and evolving character. It is not a stagnant void, but a canvas on which the universe paints its own story, a story that began with the explosive birth of the cosmos. Does the vacuum of space contain any particles or fields? The question of whether the vacuum of space is actually emptiness, free of particles or fields, is a cornerstone of advanced cosmology. At first glance, one might be tempted to view the vacuum of space as an empty void, a vast expanse devoid of matter or energy. But as we delve into the deeper world of quantum mechanics, we encounter a remarkable revelation. The vacuum is not as empty as our classical intuition suggests. Quantum mechanics, the framework that governs the behavior of particles at the smallest scales, reveals a world of extraordinary activity within the supposed void of space. Here, the vacuum is far from still, teeming with what scientists call quantum fluctuations. These fluctuations are similar to the subtle ripples on the surface of a calm pond, only they occur at a subatomic level. Within these quantum fluctuations, particles and their antiparticles enter into a fleeting and short-lived dance of existence. They arise spontaneously from the vacuum, only to collide and annihilate each other in a brief cosmic ballet. These transient events contradict our classic understanding of emptiness and reveal a dynamic and ever-changing web within the vacuum. In addition, the vacuum of space is not just a passive background, but an integral actor in the cosmos. It houses fields that govern the fundamental forces of the universe, such as the electromagnetic field. These fields extend through space and penetrate even regions that we might perceive as empty. In the field of advanced cosmology, it becomes clear that the vacuum of space is far from a true void. It is a dynamic arena where the line between nothing and something is blurred. The vacuum is alive with the quantum fluctuations of particles and fields, challenging our preconceptions about emptiness. Furthermore, this concept has practical implications. Scientists harness the inherent energy of these quantum fluctuations through a phenomenon known as the Casimir effect. When two parallel conductive plates are placed close together in a vacuum, they experience a tiny but measurable attraction due to the suppression of certain vacuum fluctuations between them. This effect, although subtle, demonstrates the tangible consequences of nothingness in a vacuum. What role does dark matter play in the idea of nothingness in the universe? Dark matter, that elusive substance that makes up a significant portion of the universe's mass, weaves a complicated story of nothingness and the profound influence it exerts on the cosmos. Dark matter, unlike the known matter that makes up stars, planets, and galaxies, remains invisible to our senses. It refuses to interact with light, making it undetectable by conventional observations. Yet their gravitational presence is undeniable and exerts a powerful influence on the cosmic stage. This paradoxical nature makes dark matter a prime candidate for exploring the role of nothingness in the universe. In the vast cosmic web, where galaxies are arranged like jewels in the night sky, dark matter forms the hidden framework that underpins the visible universe. She occupies the cosmic voids and weaves invisible threads that connect galaxies and serve as the cosmic glue that holds them together. This connection between galaxies would be impossible without the presence of dark matter, a substance hidden in the fabric of space. The role of dark matter becomes even more fascinating when we consider the cosmic dance of galaxies. As they rotate within clusters of galaxies, the gravitational force of the visible matter alone would not be enough to keep them from drifting apart. It is the invisible hand of dark matter that, with its immense gravitational force, prevents these galaxies from scattering into the cosmic voids. In this sense, dark matter transforms the apparent emptiness of space into a dynamic stage on which galaxies perform their celestial dance. Furthermore, the idea of nothingness takes on new dimensions when we look at the universe on the largest scales. Computer simulations and observations show huge cosmic filaments, like tendrils of a complicated cosmic web, in which dark matter is concentrated. These filaments guide the flow of normal matter and orchestrate the formation of galaxies and the distribution of large-scale cosmic structures. In these seemingly empty spaces, dark matter is the architect, shaping the fundamental framework of the universe. The role of dark matter in the concept of nothingness transcends mere emptiness. It reminds us that in the cosmic voids and the apparent vastness of space, there exists an invisible but powerful presence that influences the fate and structure of the cosmos. Dark matter challenges us to consider the profound interaction between nothingness and the hidden forces that shape the universe, underscoring that even in the seemingly emptiest regions of the cosmos, there is far more than meets the eye. Can space ever truly be empty? The answer lies in the persistent whispers of the cosmic background radiation, a phenomenon that challenges our concept of absolute nothingness. The cosmic background radiation, often referred to as the cosmic microwave background radiation, CMB, serves as an indelible relic from the earliest moments of our universe. It is the afterglow of the Big Bang itself, a cosmic echo reverberating through the cosmos and a testament to the lasting legacy of the original explosion that gave birth to our universe. To understand the connection between nothingness and the cosmic background radiation, we need to travel back in time, some 13.8 billion years ago. At this point in cosmic formation, the universe was a bubbling cauldron of energy and matter, unimaginably hot and dense. Photons, the particles of light, were continuously emitted and absorbed in a turbulent dance that created a blinding opaque nebula that obscured the contents of the universe. As the universe expanded and cooled, about 380,000 years after the Big Bang, a remarkable transformation took place. The universe went from a state of almost infinite energy and density to a state of relative calm. Photons, once tightly intertwined with matter, gained the freedom to move through space without constantly interacting. This cosmic event is called recombination. The photons, now free from the shackles of matter, began a timeless journey through the ever-expanding universe. Today we perceive it as the cosmic microwave background radiation, a faint glow of microwave radiation that fills every corner of the cosmos. It is as if the universe carries within itself a silent memory of its fiery birth. This background radiation, bathing the cosmos at a frigid temperature of about 2.7 degrees above absolute zero, 454.81 degrees Fahrenheit, or 270.39 degrees Celsius, is a testament to the idea that space can never be truly empty. Even in the most desolate and remote regions of the universe, the echo of the Big Bang persists. The discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson marked a turning point in our understanding of the history of the universe. It provided convincing evidence for the Big Bang theory and confirmed the existence of a cosmic framework that goes far beyond the visible matter in the universe. So when we consider whether space can ever be truly empty, the cosmic background radiation serves as a powerful reminder that even in the apparent voids of the cosmos, traces of its living past remain. How do quantum fluctuations challenge the concept of absolute nothing? At the quantum level, where particles and forces interact in a ballet of probabilities, nothingness becomes a dynamic and living arena. Quantum mechanics, the branch of physics that governs the behavior of particles at the smallest scales, reveals a fundamental truth. Even in the absence of matter or energy, the vacuum of space is far from empty. Quantum fluctuations, similar to the gentle ripples on the surface of a calm pond, are the essence of this cosmic activity. In the seemingly empty vacuum of space, particles and their antimatter counterparts arise spontaneously, form briefly, and then annihilate in a dance of creation and destruction. These fleeting events are governed by Heisenberg's uncertainty principle, which allows particles to cross the boundaries of nothingness for a short time, emerging from nothingness and then falling back into it. These quantum fluctuations challenge the concept of absolute nothingness, as they give the vacuum a noticeable energy and vibrancy. It is as if the vacuum has a latent vitality in which particles emerge from nothing and return to it, leaving a subtle imprint on the fabric of space. Quantum fluctuations are not just theoretical abstractions. They have practical consequences and influence the behavior of particles and fields at the quantum level. For example, they give rise to the phenomenon of vacuum energy, a form of energy inherent in the vacuum itself. This vacuum energy plays a role in the accelerated expansion of the universe, as observed by cosmic measurements. Are there regions in space where the density of matter is extremely low and approaches nothing? To answer this question, we must first recognize the astonishing diversity of cosmic landscapes. Our universe is a fabric woven from the fabric of matter and energy, a complex web of galaxies, stars, and celestial phenomena. But amidst this cosmic splendor, we find regions where the density of matter drops to levels that exceed our earthly comprehension. One such realm is the vast cosmic voids, vast, seemingly empty pockets within the cosmic fabric. In these voids, galaxies are rare, and the density of matter is significantly lower than in the busy galactic neighborhoods. These gigantic voids span millions of light years, and to a casual observer might appear to be cosmic deserts approaching a state of nothingness. But the reality is more complex. Even in these vast voids where galaxies are rare, there is still a faint trace of matter. Individual galaxies, cosmic dust, and the ethereal presence of dark matter. Dark matter, a mysterious substance that makes up a significant portion of the universe's mass, exerts its gravitational influence on even the emptiest regions, weaving an invisible thread through the voids. On a larger scale, the universe itself is expanding, and this expansion has profound implications for the concept of nothingness. As galaxies move apart due to the expansion of the universe, regions that were once filled with matter become more sparsely populated. The density of matter in these regions decreases over cosmic time, approaching a state that could be perceived as nothing compared to the densely populated regions of the cosmos. Yet even in the most sparsely populated cosmic expanses, a subtle presence remains. Photons of light traveling through the cosmos, the cosmic microwave background radiation, and the quiet whispers of primordial particles. These traces, although extremely faint, remain and remind us that even in the most remote and empty reaches of the universe, the concept of nothingness is difficult to define absolutely. Is there a connection between the concept of nothingness and the expansion of the universe? The idea of nothing is linked to one of the most profound cosmic phenomena, the expansion of the universe. This connection reveals a fascinating story that captivates our imagination and reveals the intricate interplay between the concept of emptiness and the evolution of the cosmos. Our journey begins with a fundamental insight. The universe is not static, but dynamic. Galaxies, like celestial islands, are not fixed in space but are constantly moving apart. This cosmic choreography, known as the expansion of the universe, is a crucial piece of the puzzle that links the concept of nothingness to the vast cosmic expansion. The story of this connection unfolds as we look into the distant past, some 13.8 billion years back. The universe experienced an event of monumental significance, the Big Bang. It marked the explosive birth of our universe from a singularity, a point of infinite density and temperature. At that precise moment, the universe was devoid of the structures and matter we observe today. It was, in a sense, a state of cosmic nothingness. When the universe exploded into existence, it was unimaginably hot and dense, a bubbling cauldron of energy and radiation. In the early moments, particles and forces interacted in a cosmic symphony beyond our earthly understanding. But as the universe expanded, it began to cool and entered a phase known as recombination about 380,000 years after the Big Bang. A transformative event occurred during recombination. At this point, the temperature of the universe dropped so low that electrons combined with protons to form the first hydrogen atoms. This marked the transition from a plasma of charged particles to a neutral, transparent gas. For the first time, the cosmos became a place where light could travel through space without being constantly scattered. This transition is key to understanding the connection between nothingness and the expansion of the universe. It allowed light to travel freely through space, carrying with it the earliest photons, the cosmic microwave background radiation. Today, these photons penetrate every corner of the universe and serve as a lasting relic of the Big Bang. The cosmic microwave background radiation is essentially a snapshot of the universe's past, a time capsule from an era when the cosmos was a seething sea of energy and matter. Their existence and the fact that we can observe them underscores the profound connection between the concept of nothingness in the creation of the universe and the ongoing expansion of the cosmos. How does the concept of nothingness in space relate to the formation of galaxies and stars? To understand this connection, we must first consider the primordial state of the universe, moments after the Big Bang, a cataclysmic event that marked the birth of the universe about 13.8 billion years ago. At that moment, the cosmos was a blazing hot, rapidly expanding sea of energy and fundamental particles, a state of extreme density and temperature. But as the universe continued to expand and cool, gravity emerged as the dominant force and led to the formation of structures. These structures began as tiny fluctuations in the density of matter within the early primordial soup of the universe. These fluctuations, although tiny, had profound implications for the future. As the universe aged, gravity gently pulled matter together into regions where these fluctuations were slightly denser than their surroundings. Over epochs, these regions grew and formed the cosmic framework for galaxies. It is as if the seeds of galaxies were sown in the fabric of space itself. Within this apparent void, gas and dust gradually accumulated, forming vast clouds of matter. Gravity's incessant pull caused these clouds to continue to condense, eventually leading to the birth of stars. Nuclear fusion ignited in the hearts of these newborn stars, bathing the cosmos in the warm light of the stars. Galaxies, each consisting of billions or even trillions of stars, formed as cosmic cities within the vast cosmic voids. These galaxies, ranging from elegant spiral galaxies to enigmatic elliptical galaxies, became the epicenters of cosmic activity, and their gravitational interactions determined the fate of the universe. The concept of nothingness in space, far from representing emptiness, thus turns out to be a canvas on which the magnificent web of galaxies and stars is woven. It is the expanse between the cosmic structures that allows these entities to exist. Indeed, without the apparent emptiness of space, galaxies and stars would not have the cosmic stage on which to perform their celestial dance. The connection between nothingness and the formation of galaxies and stars underlines the complexity of the cosmos, in which emptiness appears not as a vacuum, but as a necessary background against which the cosmic narrative unfolds. Does the absence of matter in certain parts of space contribute to the formation of black holes? Black holes, often described as cosmic abysses from which nothing can escape, are formed by a complex interplay of gravity and the absence of matter. These enigmatic celestial objects have long captured the imagination of astronomers and scientists, serving as portals to the core of advanced cosmology. The journey to understanding the connection between nothingness and black holes begins with massive stars. Stars, those brilliant beacons in the night sky, have a limited lifespan. When a massive star reaches the end of its nuclear fuel, it undergoes a cataclysmic event known as a supernova. The star's core collapses under the force of gravity, creating an incredibly dense and compact region. In these stellar death throes, when the core mass exceeds a critical threshold, it cannot withstand the incessant pull of gravity. In an instant, the core collapses and condenses into an infinitesimal point of infinite density, an event known as gravitational collapse. At that moment, nothingness becomes a cosmic crucible for the birth of a black hole. As the core collapses, it forms a region of gravity so intense that not even light can escape its clutches. This point of no return is called the event horizon and marks the boundary between the observable universe and the mysterious realm of the black hole. Black holes come in a variety of sizes, from stellar black holes, which form from the remnants of massive stars, to supermassive black holes, which are found at the centers of galaxies and contain millions or even billions of times the mass of our Sun. However, the process of their creation remains rooted in the absence of matter in certain regions of space. In regions of space where matter is scarce, such as the voids between galaxies, the conditions for black hole formation are rarer, but not impossible. Stellar collisions and interactions in these barren regions can lead to the formation of massive stars, setting the stage for future black holes. Furthermore, the vast cosmic landscape provides ample opportunities for the birth of supermassive black holes. These giants probably emerge over cosmic epochs as matter falls towards them and gradually builds up their colossal mass. Are there philosophical debates about the idea of nothingness in space and its implications? The philosophical debates about nothingness in space recall age-old questions about the nature of existence, the origins of the universe, and the nature of reality. At the heart of these debates is the fundamental question: can nothing truly exist, or is it just a conceptual vacuum that our minds create to cope with the absence of matter and energy? One perspective holds that the nothingness in space is not empty space, but a complex web of quantum fluctuations, subtle ripples in the fabric of space-time, and the remnants of cosmic phenomena. In this view, even the seemingly emptiest regions of the cosmos are filled with quantitative activity that challenges the idea of a true vacuum. On the other hand, another philosophical viewpoint suggests that nothingness represents the absence of existence itself, a concept that is beyond human understanding. It raises questions about the true nature of nothingness and whether it can be scientifically defined or quantified. These philosophical debates also extend to the implications of nothingness in space. They ask us to consider the role of the void in the grand narrative of the cosmos. Does the apparent emptiness of space serve as a canvas on which the universe paints its complicated history? Or is it a cosmic vacuum that invites us to explore the limits of human understanding? Furthermore, the concept of nothingness in space links to age-old questions about the existence of extraterrestrial life and the potential habitability of distant planets. Philosophers and scientists are considering whether regions of apparent cosmic emptiness could harbor life beyond our planet, raising profound questions about the nature of life itself. How has our understanding of nothingness in the cosmos evolved over time through scientific discoveries and theories. The concept of nothingness was often linked to philosophical and theological reflections and shrouded in the mystery of heaven. The skies seemed to have a certain stability and order, with little room for the idea of cosmic emptiness. But with the beginning of the scientific revolution, humanity's gaze shifted from the realm of the abstract to the empirical. Pioneering astronomers like Galileo Galilei pointed their telescopes at the sky and revealed a cosmos teeming with celestial bodies. This newfound observation precision destroyed the old ideas of an empty universe. As the 20th century ushered in a new era of scientific inquiry, the concept of nothingness in the cosmos underwent a remarkable transformation. The development of the theory of relativity by Albert Einstein and quantum mechanics by Max Planck and others produced revolutionary insights. Einstein's equations revealed the dynamic nature of space-time, while quantum mechanics illuminated the quantum fluctuations that permeate even the seemingly emptiest regions of space. One of the pivotal moments in the development of our understanding of nothingness was the discovery of the cosmic microwave background radiation in 1965. Arno Penzias and Robert Wilson discovered this faint afterglow of the Big Bang, a microwave echo reverberating through the cosmos. It provided compelling evidence for the Big Bang theory and changed our perception of the early universe. Further advances, such as the development of the inflation theory of the universe, proposed by physicist Alan Guth in 1980, expanded our understanding of the cosmos. This theory postulates that the universe underwent rapid and exponential expansion in its early moments, providing a compelling explanation for the observed large-scale structure of the universe. Additionally, the study of dark matter and dark energy, two mysterious components that make up most of the universe's mass and energy, has deepened our appreciation for the nothingness in the cosmos. These invisible, enigmatic entities exert their gravitational influence and shape the fate of the universe, challenging our notion of emptiness. Today, our understanding of nothingness in the cosmos is shaped by a deep appreciation for the complicated interplay between the visible and the invisible, the known and the mysterious. Advanced cosmology has led us to recognize that even the most remote regions of space contain traces of cosmic activity, from quantum fluctuations to the echoes of the Big Bang. What does nothing look like or feel like? At first glance, it may seem paradoxical to think about the look or feel of nothing, since by definition it implies the absence of any perceivable properties. Yet in this paradox lies a profound opportunity for exploration and contemplation. In the cosmos, the concept of nothingness often evokes images of vast, dark voids, where the absence of matter and energy creates an apparent void. These cosmic voids, stretching across millions of light years, could evoke a feeling of loneliness and silence, a vast expanse where the universe seems to be missing. But this apparent emptiness can be deceiving. Even in the most desolate regions of space, a subtle web of activity exists. Quantum fluctuations, the gentle waves in the quantitative fabric of spacetime, create fleeting particle-antiparticle pairs that briefly appear and disappear, leaving a trace of their presence. These fluctuations, although imperceptible to our senses, are a testament to the complicated dance between nothingness and the quantum world. They remind us that even in the seemingly emptiest spaces, the cosmos is alive at the smallest level and challenges our understanding of emptiness. From a philosophical perspective, asking what nothing looks or feels like can lead to introspective reflections. Some might argue that the mere act of perceiving or feeling nothing presents a paradox, since the act of perceiving presupposes the existence of something being perceived. In the realm of advanced cosmology and science, our understanding of the concept of nothing requires a delicate balance between empirical observation and abstract contemplation. It challenges us to explore the limits of human cognition and to reflect on the limits of our sensory perceptions. How do human perception and cognition influence our ability to grasp the concept of nothingness in the cosmos? Human perception, formed by our sensory organs, plays a crucial role in our understanding of the universe. We perceive the cosmos through the lenses of our eyes, ears, and other sensory organs that have evolved to interpret the physical world. But when it comes to understanding the concept of nothingness in the cosmos, our senses encounter profound limitations. Consider the vast cosmic voids that stretch across the universe, seemingly devoid of matter and energy. To our eyes, these regions appear as inky darkness, a void broken only by distant points of starlight. But this apparent emptiness belies the intricate quantum fluctuations and imperceptible activity that take place in even the most desolate reaches of space. Our senses, finely tuned to the terrestrial world, struggle to grasp the subtle quantum phenomena that underpin the cosmos. Quantum fluctuations, the fleeting waves in the quantitative fabric of space-time, remain beyond the reach of our perception. These fluctuations, although minute, are an integral part of the cosmic fabric and challenge our ability to truly grasp the concept of nothingness. Cognition, the realm of thought and abstract thought, further complicates our search for understanding nothing. When we think about the nature of nothingness in the universe, we navigate the complicated landscape of philosophy, mathematics, and conceptual thinking. Philosophical investigations of nothingness invite us to explore the limits of human thought. Can nothing really exist, or is it just a conceptual construct? How do we reconcile the absence of matter and energy with the persistence of quantum fluctuations and cosmic forces? Mathematics, a powerful tool for modeling the cosmos, offers its own insights into the concept of nothingness. In the field of mathematics, zero represents the absence of quantity, a numerical representation of nothingness. Yet even within this mathematical abstraction, we encounter the enigma of infinity, an abstract concept that transcends human intuition. How can we use technology to go beyond our human limitations? One of the main ways technology extends our reach is through the development of powerful telescopes and observatories. These marvels of engineering serve as cosmic time machines, allowing us to peer into the past and view distant galaxies, stars, and cosmic events. They capture light that has traveled across the vast universe for billions of years, offering us glimpses into the universe's distant past. Take, for example, the Hubble Space Telescope, a technological marvel that orbits the Earth. It provides us with breathtaking images of galaxies, nebulae, and other celestial bodies and offers us insights into the size of the universe. With its advanced instruments, Hubble has revealed the secrets of distant galaxies and shed light on their formation, evolution, and the presence of supermassive black holes at their centers. Similarly, Earth-based observatories, equipped with cutting-edge technology, allow astronomers to discover and analyze cosmic phenomena that escape our unarmed senses. Radio telescopes, for example, receive radio waves from celestial sources and reveal hidden details about the universe, including the cosmic microwave background radiation, a relic of the Big Bang. In addition, the technology allows us to explore the cosmos through robotic missions and space probes. These remarkable instruments penetrate the harsh, radiation-filled reaches of space where human presence is impossible. They collect data, take images, and conduct experiments, expanding our understanding of celestial bodies and their environments. One such mission is the Mars rovers, which have traversed the Martian landscape studying the planet's rocks, soils, and geology. These robotic explorers have become our eyes and hands on another planet, sending valuable data to Earth and igniting the imaginations of millions. Furthermore, the advancement of supercomputing technology has revolutionized our ability to model and simulate complex cosmic phenomena. These powerful computers process huge amounts of data and allow us to simulate the behavior of galaxies, stars, and even the early universe. Through simulations, scientists gain insights into the complex dynamics of cosmic structures and expand the boundaries of our knowledge. Now let's take a closer look at the recently launched James Webb Space Telescope. The James Webb Space Telescope, often referred to as JWST or Webb, stands as a testament to human engineering and scientific ambition in the field of advanced cosmology and space exploration. Designed to rewrite the handbook of our cosmic understanding, this cutting-edge telescope represents a monumental achievement in both engineering and scientific endeavor. Started on the 25th. In December 2021, aboard an Ariane 5 rocket, the JWST began its journey to the second Lagrange point, about 1.5 million kilometers from Earth. Strategically chosen for its unique characteristics, this particular location provides a stable environment, largely free from the disturbances of Earth's atmosphere and the overwhelming glare of the sun. Such conditions are essential for the telescope's precise observations in the infrared region, a region of light invisible to the human eye. The primary purpose of the James Webb Space Telescope is to revolutionize our understanding of the cosmos by exploring the universe in unprecedented detail and depth. Unlike its predecessor, the Hubble Space Telescope, which observes primarily in visible and ultraviolet light, the JWST is specifically designed to observe in the infrared. This ability gives him the power to reveal cosmic phenomena that were previously hidden in darkness and mystery. The JWST is equipped with an array of advanced scientific instruments and detectors that allow it to peer through cosmic dust clouds and reveal the birthplaces of stars and planetary systems. Its sharp infrared vision can detect the faint glow of distant galaxies, allowing astronomers to study the early epochs of the universe shortly after the Big Bang. By analyzing the light from these distant galaxies, the telescope will provide insights into the formation and evolution of galaxies over cosmic time. In addition, The JWST is ready to unlock the secrets of planetary systems beyond our solar system. It will study exoplanets and their atmospheres, providing crucial data to identify potentially habitable worlds and advance the search for extraterrestrial life. Its capabilities extend to characterizing the composition and conditions of exoplanets and paving the way for groundbreaking discoveries in the search for habitable environments beyond Earth. Furthermore, the telescope's precise instruments make it possible to penetrate the secrets of the dark side of the universe. It will examine the nature of dark matter and dark energy, enigmatic components that make up most of the cosmos but remain invisible to our senses. This pursuit has the potential to reshape our understanding of the fundamental forces and components that govern the universe. Essentially, the James Webb Space Telescope is an engineering marvel, a testament to human endurance, and a beacon of hope for those seeking to explore the cosmic unknown. Its mission is not only to answer existing questions, but also to raise new ones and take us further into the unexplored areas of the universe. Now let's go beyond our current understanding. As technology advances and telescopes like the JWST are launched, our search for extraterrestrial life in the cosmos continues. What if we found life? Could we possibly find the answers we seek? In recent years, there has been a surge of excitement and anticipation surrounding the discovery of exoplanets, planets orbiting stars outside our solar system. These exoplanets, numbering in the thousands, were identified through the tireless work of space telescopes and observatories, such as NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS. The staggering number of exoplanets raises a compelling question. Could some of these distant worlds have conditions that support life as we know it? Scientists have identified a subset of exoplanets that reside within their star's habitable zone, often called the Goldilocks zone. These planets lie at a distance from their stars, where temperatures may support liquid water, a crucial ingredient for life on Earth. To determine the potential habitability of exoplanets, astronomers use a variety of techniques, including studying exoplanets' atmospheres, surface conditions, and the presence of chemical compounds that could indicate life processes. For example, the James Webb Space Telescope, JWST, with its advanced instruments, promises to revolutionize our ability to analyze the atmospheres of exoplanets and search for biosignatures, such as oxygen and methane, that could indicate the presence of life. Interestingly, the discovery of exoplanets has revealed a variety of planetary environments, from hot gas giants to rocky worlds with Earth-like properties. Some of these exoplanets could have conditions very different from those of Earth, challenging our ideas about where and how life might thrive. One of the most significant breakthroughs in the search for extraterrestrial life was the discovery of exoplanets in binary star systems, in which two stars orbit each other. Such environments were once considered uninhabitable for life, but recent discoveries have expanded our understanding of potentially habitable niches. In addition, the field of astrobiology, which combines knowledge from astronomy, biology, and chemistry, studies the extreme life forms on Earth. including extremophiles that thrive in hostile environments. These extremophiles offer insights into how life might adapt and persist on exoplanets with harsh conditions. Now let's talk about one of the many exoplanets we humans have discovered, Proxima b. Proxima b, the enigmatic exoplanet located in the habitable zone of the star, Proxima Centauri, invites us to explore the mysteries of distant worlds beyond our solar system. In the field of advanced cosmology and science, Proxima b stands as a testament to our insatiable curiosity and incessant drive for knowledge about the cosmos. Discovered in 2016, Proxima b quickly caught the attention of astronomers and space enthusiasts alike. It orbits the closest star to our Sun, Proxima Centauri, and is about 4.24 light-years from Earth. To put this astronomical number in perspective, 1 light-year is approximately 5.88 trillion miles, making Proxima b's location a cosmic stone's throw away. Proxima b's position within the habitable zone, often called the Goldilocks zone, tantalizingly suggests that conditions on this distant world may be favorable for life as we know it. This orbital sweet spot implies that Proxima b receives just the right amount of stellar radiation to maintain liquid water on its surface, a crucial ingredient for the emergence and maintenance of life. Despite its proximity to Earth, direct observations of Proxima b remain a formidable challenge. Its parent star, Proxima Centauri, is a red dwarf that is significantly fainter and cooler than our Sun. This small star casts a faint light on its planetary companion, complicating our attempts to study the exoplanet's properties. To gain insight into the nature of Proxima b, astronomers are using a variety of innovative techniques. One approach is to monitor the star's subtle fluctuations caused by gravitational interaction with the orbiting exoplanet. By measuring these fluctuations, scientists can estimate Proxima b's mass and infer its orbital properties. Another study method uses observation of starlight traveling through the atmosphere of Proxima b as it passes in front of its host star. This technique provides a way to analyze the planet's atmosphere, potentially revealing chemical compositions, temperature gradients, and the presence of biosignatures. Additionally, the James Webb Space Telescope, JWST, poised to redefine our exploration of exoplanets, offers the opportunity to study Proxima b in unprecedented detail. Equipped with advanced infrared instruments, the JWST is expected to assess the exoplanet's atmosphere and look for clues about its habitability. We've now talked a little about exoplanets and how they could change our view of extraterrestrial life in the cosmos. But let's return to the question of this video. What is nothing? Can we humans really understand what nothing really is? In our search for an answer, we may first need to figure out how everything ends, how our universe ends. One of the most discussed hypotheses regarding the fate of the universe is known as the Big Freeze, or heat death. This scenario is based on the concept of the expansion of the universe, first discovered by astronomer Edwin Hubble in the early 20th century. The Big Freeze suggests that the universe will continue to expand indefinitely, causing galaxies to move further and further apart. As the universe expands, the space between galaxies stretches, causing a decrease in temperature and energy density. Stars, the cosmic engines that power galaxies, will eventually exhaust their nuclear fuel and fade into darkness. As a result, the universe is gradually becoming colder and darker, with temperatures approaching absolute zero. In this icy future, matter and energy will become increasingly dispersed, making it increasingly difficult to form complex structures such as galaxies and stars. Eventually, even atoms will decay, and the universe will be dominated by particles like electrons and positrons, floating in a sea of darkness. This state of maximum entropy and minimum energy is what scientists call the heat death of the universe. Another intriguing option is the Big Crunch. This scenario suggests that the expansion of the universe could potentially reverse at some point, causing all matter and energy to contract back into a singularity, similar to the conditions that existed at the time of the Big Bang. This cyclical model suggests that the universe experiences an infinite series of expansions and contractions. However, recent observational data from the study of cosmic acceleration and dark energy suggests that the Big Crunch scenario is less likely. Instead, the expansion of the universe appears to be accelerating, suggesting a different fate for our cosmos. Another hypothetical scenario is the Big Rip. In this scenario, the expansion of the universe accelerates to such an extreme that galaxies, stars, planets, and even atoms are eventually torn apart. The fabric of space itself disintegrates as expansion continues unabated. Although this concept is speculative, it raises intriguing questions about the ultimate fate of the cosmos. Exploring the ultimate fate of the universe, whether through scenarios such as the Big Freeze, Big Crunch, or Big Rip, provides valuable insight into the concept of nothingness in cosmology. While these scenarios describe very different outcomes, they all touch on the fundamental question of how the structure of the universe, matter, and energy might evolve over cosmic time. A central aspect of understanding nothingness in the context of these scenarios is the concept of entropy, a measure of disorder and randomness in a system. The Big Freeze scenario, for example, is linked to the idea of maximum entropy, where the universe reaches a state of ultimate disorder and minimal available energy. In this sense, nothing can be seen as the absence of organized structures such as galaxies, stars, and even particles. In contrast, the ideas of a Big Crunch or a Big Rip suggest the possibility of a reversal or rapid transformation of the universe, challenging our conventional notions of nothingness. It challenges us to consider what might exist beyond our current cosmic understanding, particularly in the context of theories of additional dimensions or multiverses. Studying these cosmic scenarios also highlights the importance of dark energy and its role in shaping the fate of the universe. Dark energy, a mysterious force responsible for the accelerated expansion of the universe, is a concept that pushes the boundaries of our understanding. By penetrating the properties of dark energy and its influence on cosmic evolution, scientists strive to gain a deeper understanding of the fundamental forces in the cosmos. Furthermore, Exploring these scenarios informs our understanding of the underlying principles of the universe, the behavior of space-time, and the nature of matter and energy. This knowledge, in turn, contributes to our ability to define and conceptualize nothingness in the context of the cosmos. When we think about nothing, we think of something empty or something that does not exist. But what about time? Time always moves, or does it? Is time a fundamental aspect of the universe, or a human invention to make us understand reality? One perspective holds that time is an inherent and fundamental property of the universe. This view is consistent with our everyday experiences, in which time flows seemingly inexorably from the past to the present to the future. From the rhythmic ticking of a clock to the changing seasons, our lives are intertwined with the passage of time. In this sense, time is an inescapable dimension of our reality that determines the unfolding of events and processes. In the field of modern physics, time is a fundamental component of space-time, a four-dimensional framework that connects the three dimensions of space with the dimension of time. Albert Einstein's theory of relativity, rigorously tested and confirmed through experiments, treats time as a dynamic and malleable entity. According to the theory of relativity, the structure of space-time is not fixed, but can be influenced by mass, gravity, and speed. This perspective reinforces the idea that time is an inherent element of the universe, intimately intertwined with the geometry of space-time itself. Conversely, there is a philosophical point of view that questions the absolute nature of time. He suggests that our perception of time as a linear and unidirectional progression is a construct of the human mind. One of the central tenets of Einstein's theory of relativity is the concept of time dilation. Time dilation means that time can pass at different speeds for observers in different states of motion or in different gravitational fields. This phenomenon has been confirmed experimentally and has practical implications for technologies such as the Global Positioning System, GPS, where satellites in orbit experience slightly different gravitational fields and therefore must take relativistic effects into account to provide accurate position information. Time dilation is particularly pronounced in regions of strong gravitational fields, such as those near massive celestial objects such as black holes. As an observer approaches a black hole's event horizon, the point of no return, time appears to pass dramatically slower for that observer compared to an observer further away. This effect is known as gravitational time dilation and is a consequence of the curvature of space-time caused by massive objects, as described by Einstein's general theory of relativity. Another region of the universe where time runs differently is the cosmic expansion. The universe itself is expanding, and this expansion affects the passage of time. As the universe expands, the galaxies and objects within it move away from each other, causing the light they emit to undergo a redshift. This redshift affects not only the observed color of light, but also the frequency and passage of time itself. Observers in different galaxies could perceive the flow of time differently due to cosmic expansion. Furthermore, in the field of quantum mechanics, the behavior of subatomic particles can challenge our intuitive understanding of time. Quantum phenomena such as entanglement and superposition suggests that particles can exist in multiple states simultaneously, undermining the classical idea of time as a linear sequence of events. Could time travel be theoretically possible, and what paradoxes and challenges does it pose? In the field of theoretical physics, there are several theories that suggest that time travel could be theoretically possible, although its realization represents an immense technological and scientific challenge. Some of the most notable concepts fueling discussions about time travel include wormholes. A popular idea is that traversable wormholes, hypothetical tunnels through space-time, could provide shortcuts to various points in time and space. Theoretical physics allows for the existence of wormholes, but their creation and stabilization would require exotic and currently unknown forms of negative energy matter. Closed time-like curves, CTCs. Some solutions to Einstein's equations of general relativity allow the existence of CTCs, orbits in space-time that repeat themselves and could potentially allow closed loops in time. However, entering and navigating these CTCs would require exotic matter with negative energy and raise paradoxes. The butterfly effect. This idea states that even small changes in the past could lead to profound and unpredictable consequences in the future. A time traveler stepping on a butterfly in the distant past could inadvertently change the course of history in unpredictable ways. The bootstrap paradox. This paradox involves an object or information being sent back in time in such a way that it itself becomes what was originally sent. For example, a time traveler might give Shakespeare a copy of his own works, which Shakespeare then publishes, a paradox that raises the question of where the original work came from. Conservation of energy and causality. Time travel could potentially violate fundamental principles such as conservation of energy and causality. Changes in the past could break the causal chain of events and create logical inconsistencies. The Novikov self-consistency principle. This principle, proposed by physicist Igor Novikov, states that the laws of nature would behave in such a way as to prevent actions in the past that would create paradoxes. In other words, if time travel were possible, the universe would ensure that paradoxes were avoided. While these paradoxes and challenges present significant obstacles to the practical realization of time travel, they also serve as fascinating food for thought. Now let's talk about the theory of multiverses. Could it help us understand what time and space really are? At its core, the theory of multiverses postulates that our universe, which we perceive as the vast space of stars, galaxies, and cosmic phenomena, is not the only universe that exists. Instead, it suggests the existence of a multiverse, a vast and diverse ensemble of universes, each with its own unique physical laws, constants, and properties. One of the most prominent versions of the multiverse theory is the many worlds interpretation of quantum mechanics. This interpretation states that every quantum event with multiple possible outcomes results in a bifurcation of the universe, creating a multitude of parallel universes, each representing one of the potential outcomes. In this view, the universe is constantly splitting into an unimaginable number of branches, encompassing every conceivable outcome of quantum interactions. Another aspect of the multiverse theory comes from cosmological models, such as inflationary cosmology. According to these models, the early universe went through a period of rapid expansion during which different regions of space expanded at different rates. In some regions, the expansion stopped, allowing the formation of galaxies and stars, while in others it continued indefinitely, creating bubble universes with different physical properties. The concept of a landscape of possible universes within string theory also contributes to multiverse theory. String theory proposes that there are numerous possible configurations for the fundamental building blocks of the universe, leading to the idea that our universe is just one of many possible configurations within this vast landscape. Would it ever be possible for us humans to find an answer to the multiverse theory? Although the multiverse theory offers exciting possibilities, testing it presents formidable challenges due to its inherent nature. The main obstacles to testing the multiverse theory include cosmic isolation. The universes within a multiverse are often viewed as causally separate from one another, meaning that events in one universe would have no direct impact on another. This cosmic isolation makes it extremely difficult to observe or interact with other universes. Lack of direct evidence. To date, there is no direct observation or experimental evidence for the existence of parallel universes. The multiverse theory is largely theoretical and based on complex mathematical models, which makes it difficult to test empirically. Cosmic scale. The vastness of the multiverse, if it exists, is beyond our current observational range. The sheer size of potentially infinite universes scattered across the cosmos poses a logistical challenge when collecting data or conducting experiments. Despite these challenges, some researchers are exploring indirect ways to test aspects of the multiverse theory. Cosmic microwave background radiation, CMB. Studying variations in the cosmic microwave background radiation, the afterglow of the Big Bang, could offer insights into the existence of other universes. Anomalies or patterns in the CMB could potentially indicate collisions or interactions with other universes during cosmic inflation. String theory and particle physics. String theory, a framework that encompasses the concept of the multiverse, could offer potential predictions or constraints that could be tested through high-energy particle physics experiments. Providing evidence for string theory or specific particles consistent with its predictions could indirectly support aspects of multiverse theory. Multiverse-specific phenomena. If multiverse theory predicts the existence of unique phenomena or physical constants in other universes, then identifying these constants or observing such phenomena could provide indirect evidence. In essence, although direct confirmation of the multiverse theory remains a formidable scientific challenge, researchers are actively exploring avenues within the limits of current knowledge and technology. Hopefully, we will find an answer to this within our lifetime. We've now talked about various space and time theories, so let's address the final topic. The universe is made of matter. What exactly is matter? Essentially, matter is the material substance that makes up all physical objects, from the tiniest particles to the vast celestial bodies that populate the cosmos. Everything we see, touch and interact with, including ourselves, is made of matter. Matter is characterized by several key properties. Mass. One of the defining properties of matter is mass. Mass is the measure of the amount of matter in an object and is typically measured in units such as kilograms or grams. It determines the weight of an object and its gravitational interaction with other objects. Volume. Matter occupies space, and the amount of space it occupies is called volume. Different forms of matter can have different volumes, from the compact density of a solid to the extensive distribution of a gas. Particles. Matter is made up of tiny particles, each with their own unique properties. These particles can include atoms, molecules, and subatomic particles such as protons, neutrons, and electrons. The arrangement and behavior of these particles determine the physical and chemical properties of matter. States. Matter can exist in different states, generally categorized as solid, liquid, gas, and in some cases, plasma. These states are defined by the arrangement and movement of the particles. For example, the particles in a solid are tightly packed and have limited movements, while the particles in a gas are further apart and have greater freedom of movement. Chemical composition. Matter can be further classified based on its chemical composition. Elements, compounds, and mixtures represent different forms of matter. Elements are made up of one type of atom, while compounds are made up of different types of atoms that are chemically bonded. Mixtures are combinations of different substances that are not chemically bound. Physical and chemical properties. Each type of matter has specific physical and chemical properties that determine its behavior and characteristics. These properties include density, melting point, boiling point, conductivity, and reactivity. Matter is not a static entity, but is subject to various physical and chemical transformations. Through processes such as chemical reactions, nuclear reactions, and phase changes, matter can change from one form to another, resulting in the diverse array of substances and phenomena observed in the universe. The role of matter in the cosmos is central to our understanding of the structure and evolution of the universe. It forms the basis for celestial bodies, galaxies, stars, and planets. Furthermore, matter interacts through gravitational, electromagnetic, and nuclear forces, determining the dynamics of the universe on cosmic and quantitative scales. Now let us delve deeper into the subatomic realm and the various forms and states of matter, and reveal the intricate fabric of the material universe. Matter is made up of subatomic particles, which are the building blocks of atoms. The three primary subatomic particles are protons, neutrons, and electrons. Protons, positively charged particles found in the nucleus, center of atoms. They are crucial in defining the identity of an element. Neutrons, particles without charge that are found in the nucleus along with protons. They contribute to an atom's mass, but not its charge. Electrons, negatively charged particles that orbit the nucleus in electron clouds or energy levels. Electrons determine the chemical behavior of an atom and play a key role in chemical reactions. Elements are the purest form of matter, each consisting of a unique type of atom defined by the number of protons in its nucleus. The periodic table of elements orders all known elements by their atomic number, which represents the number of protons. Compounds are substances formed when two or more different elements are chemically combined in fixed ratios. These combinations create completely new substances with different properties. Water, H2O for example, is a compound made up of 2 hydrogen atoms and 1 oxygen atom. Mixtures are combinations of different substances that are not chemically bound. In contrast to compounds, mixtures do not have fixed ratios, and the individual components retain their properties. Examples of mixtures include air, a combination of gases, salt water, a mixture of salt and water, and even trail mix. Matter exists in different states that depend on the arrangement and movement of its particles. Solids. In solids, the particles are tightly packed, have fixed positions, and vibrate in place. Solids have defined shapes and volumes. Liquids. Liquids have particles that are more loosely packed and can slide past each other, allowing them to flow. They have a defined volume but take the shape of their container. Gases. Gases have particles that are widely spaced and move freely, filling the entire space of their container. Gases have neither a defined shape nor a defined volume. Plasma. At extremely high temperatures, matter can ionize and form a state known as plasma. Plasmas consist of positively charged ions and free electrons. Stars, lightning, and neon lights are examples of plasmas. The diversity and complexity of matter in its states and forms enable the complexity and diversity in the universe. Matter forms the basis for galaxies, stars, planets, living organisms, and everything we observe in the cosmos. Understanding the properties and behavior of matter is fundamental to our understanding of the natural world and the scientific study of the universe. In our journey through the cosmos and the intricate web of matter, we have encountered the great diversity and complexity of the material world. Yet amidst this richness, the concept of nothingness asks us to reflect on the vacuum, the absence, and the enigmatic spaces that exist between particles, objects, and even universes. From the subatomic level, where particles seemingly blink and disappear from existence in quantum fluctuations, to the cosmic level, where the vacuum of space is not truly empty but is filled with dark energy and cosmic background radiation. The concept of nothingness challenges our perceptions and inspires philosophical reflection. Is nothing merely the absence of something, or does it have its own existence and essence? Can we truly understand nothing, or does it remain an elusive and abstract concept that transcends human cognition? Thanks for watching.